Welcome everyone to this video. Uh, Today we are going to study an idea which helps us understand a lot of ideas in kinematics. So that concept is called differentiation. So differentiation is one of those things which we study uh, as a tool to understand physics. And like I said, basically it helps us in starting the chapter of kinematics. It is a pivotal topic. So, uh, we know already a lot of ideas about motion. For example, we know if there is a car, or if there is a person who is moving on a road, then that person, when he starts his journey, let's say he wants to buy apples. So when he starts moving, so he has some speed with which he is moving. And then we define that when that person comes back to his home after buying apples, uh, he took some time uh, in going to the shopkeeper, purchasing apples and paying him, and then coming back. All those things take time. But what about the instantaneous part? What happens at different time instants? And what is a time instant in itself? Time instant is basically the time at the current moment. For example, at this point of time, what is the time in your clock? That is the time instant. And how much distance we have moved, that is the distance covered. What path length we have gone through. For example, I would have taken some kind of S-shaped path as I am going to purchase the goods. So in that case, the distance would be something. And if I move in a straight line path, then distance is something else. So distance is something which is part dependent quantity. And displacement is something which is a quantity dependent upon the final point and initial point. So all those things come together in our uh, in basically helping us understand what is differentiation. So let us begin. So first of all, we want to define what differentiation is or what displacement is. This is the one thing which we want to define first. Because displacement is like that one thing which is very common in our world. Everything is getting displaced from one point to another. For example, you are drinking your morning tea. So that morning tea, when you drink it uh, in the morning, you basically want to drink it with your family and in the morning table. Whereas when you want to drink it with your friends, you have to get displaced at some other point, probably at the chai point, and then you are taking tea. We can say that the displacement of the particles of tea uh, in your body remains the same. Where if you consume the tea with your family or with your friends, is just that the person who is consuming he has changed positions. So displacement is a frame dependent quantity. With respect to you, the tea particles or the milk particles they are getting displaced the same distance. Whereas when you uh, take some other frame of reference, for example, your home frame of reference, then the displacement may vary. So, displacement we define as some quantity denoted by the symbol delta x. So, we must know what position is. Position is represented by x that you might be knowing already. So, delta x, this is what is denoting displacement. It is defined as the difference between the final position and initial position of the particles. Or we can say it is subtracting the initial position of the particle from the final position. So this is what displacement we can say. As an example, I can say if a particle is initially at 1 meters. So what does that mean? It means that a particle is simply at a distance of 1 meter in positive direction of x from some selected origin. Okay, that origin can be anywhere, and depending upon that, that particle would be 1 meter away from it. I'll draw it. Basically, this is the origin O, and in some positive direction, which I have selected like this, somewhere here, the particle is there. So this is plus 1 meters. Uh, in the same way, I can say, okay, now we have decided to move somewhere else. So the position of the particle finally, xf, is let's say some 4 meters. So we'll say that okay, the displacement of the particle, delta x, is final position minus initial position. 4 meters minus 1 meters, that is 3 meters. And now I can talk about time interval or time instants. Let's say at when the particle was at 1 meter, the time was some 0 seconds. That is, we were starting our clock. And then we have reached the position of final position we have reached. That time, the time elapsed was only 2 seconds. So we will say that the displacement of the particle divided by the time interval, they should give us something, right? What is delta t? Delta t is time interval. It is the final position, final time, that is 2 seconds. Sorry, it is the final time minus the initial time. So this final time minus initial time, this is delta t. And delta x upon delta t, this is defined as average velocity. So this is the other definition which we have to learn. What is average velocity? So average velocity is nothing but displacement of the particle per unit time or displacement upon time. So how is that important for us? Basically, we are studying differentiation. So we want to get to the instantaneous part of velocity, by which you mean that even though the particle's velocity varies a lot, it carries significance in a lot of cases. Like we can say that okay, when some kind of body is falling on Earth. So when a body is falling on Earth, it does not travel with the constant speed. In some cases, it can travel at constant speed. For example, you would have never thought about raindrops. Raindrops are one of those things which travel at a constant speed when falling on Earth. After when they uh, start from clouds, they have some zero speed unless the cloud itself is moving. When the raindrop starts accelerating towards Earth, it is gaining speed because of acceleration to gravity, and then it reaches constant speed. So it is a classic case where the particle speed is changing at different times. Whereas the thing which we are studying is average. It does not care how much speed has changed between the initial and final points, how the particle traveled. That is, with what speed it is traveling, that is not taken in account by average velocity. And that is a problem, which is solved by uh, getting to the idea or deriving an idea of instantaneous velocity. So that's why we have studied these simple things first. We have studied displacement, we have studied times. You might be knowing this already, but we have to define these things to get to the idea. Okay, what is instantaneous velocity? What is its need? So let us start with it. Like in the case of raindrops only, when the raindrops are falling on Earth, then in that case, what would be the displacement of the raindrop? Displacement of the raindrop would be some 500 meters. Let's say the cloud was half a kilometer above Earth's surface. So it has traveled 500 meters in, let's say, some 25 seconds. So what is the average speed? 500 meter upon 25 seconds, or average velocity 500 meters divided by 25 seconds. And speed and velocity, I'm just taking the same idea here. We are saying that we are considering velocity, right? So 500 meters divided by 25 seconds, that is my displacement, that is 500 meters, and divided by time, that is 25 seconds. Each raindrop is traveling with the same height, through the same height, because they are traveling on the same, from the same cloud they are descending. More or less, they will take the same time and same displacement. So it would be some 20 meters per second. Now, it does not show us the idea ke what was the instant at which the particles stopped gaining speed. It stopped increasing its speed. And by particle, I mean droplets. Right? The droplets, they would have started, after they would have started, they would have increased their speed because of gravity. But there is some other force which also acts. Gravity is one force which is pulling the particle in downward direction. By pulling it means it is accelerating it. And when air particles encounter these raindrops, they exert a force in opposite directions of its speed. This is called the viscous force. So this viscous force is the opposing force which helps us in actually decreasing the rate at which the particle speed is increasing. So that means we are concerned with the speed of the particle at an instant. That is the velocity of the particle at an instant. So this is where differentiation comes into play. Okay. So differentiation in itself, we would be defining the same thing, right? Which we have been going on about, that is instantaneous velocity. So how does differentiation come into play? It's just that we'll be taking the two uh, positions x1 and x2 and time instants t1 and t2, and we would say that okay, we already know what is average velocity, right? Let's see, if I draw a graph, what would the graph look like? The graph would look like something like this. So this is how the displacement of the particle is changing, or the position of the particle is changing like this. So at some t1 time, I would say the position of particle is x1, and I would say at some t2 time, the position of the particle is some x2, right? So at t1 time, my position is x1. At t2 time, my position is x2, right? So, okay, fine. What else? Now we want to do something. I hope it is visible. This is time t1. This is time t2. This is position x1. This is position x2. And if you can help me finding what is the average velocity in this case. So the average velocity in this case is delta x, is delta x upon delta t. This is what is average velocity. The average velocity will indicate by uh, uh, drawing the v symbol and putting these uh, braces. So this is like less than sign, greater than sign. Between that, we put this v symbol. So this is called average velocity. So this is fine. We already found our average velocity even without this graph, right? What was its value? Its value was some 20 meter per second. Now the point is that these T1 and T2 time intervals or time instants, they will be coming close to each other quite a lot. Like this T1 and T2, we want to bring them together. So what do you think we are getting at? When we bring these two times together, T1 and T2, we are trying to get to a single instant, right? Like in average velocity case, we have a time interval. Time interval means that they are two separate instants. And the definition is displacement upon time interval. If we combine these two time intervals, or if we bring these two times instants very, very close to each other, what will happen? It will show us that what is the velocity in that small time interval. Let's say that time interval is dt. This delta t, it became very small. So it became dt like this. And this delta x will automatically become very, very small. In terms of graph, I can say it like this. K at some t time. Here, I'm increasing the time interval by this dt instant. So when I increase the time by this dt instant, I would say the position has changed from x to x plus dx. Right. So if I were to apply the concept of average velocity here, that what is the average velocity between these two time instants? It would be dx by dt. So this is what is instantaneous velocity of the particle v. That is dx by dt. And how do we come about that, right? Where does d come from? Where does dx come from? So I'll tell you about it. But at first, we have arrived at the equation of instantaneous velocity, right? That's it. So what we have done is that we have said that these two time intervals, these two time instants are very, very close to each other. So as they are very, very close to each other, whatever average velocity which we have, that is dx by dt, it represents, if I divide dx, that is the displacement, with the time interval dt, then it helps me getting, or it is equal to the instantaneous velocity. So this is what instantaneous velocity is, right? Okay. So now what we will say is that, okay, we have arrived at that symbol. What is the way? How do we understand in some other way? So remember that we use this definition, right? dx by dt. So in this dx by dt, if I were to draw it diagrammatically, okay, what that is. So that dx by dt, if I draw it like this, so this particular whole length is delta x. So if I divide delta x by delta t, it's average velocity. But you know, from this triangle, this delta x upon delta t is something which you know, and you are correct. It is the slope of this line which is joining the initial instant and the final instant. That line slope is the average velocity, right? We know tan theta, if this angle is theta, then I hope that it is clear. Taking one moment here that this is the triangle. So this is the important point, right? This has to be absolutely clear if I have a triangle here. So in this triangle, this angle is theta, right? If it is not visible, just basically assume that this particular angle in the triangle is theta. That is the angle at the bottommost corner. So this angle is theta, that you know. So what would be tan theta? Tan theta would be this side, that is the perpendicular upon base. So this perpendicular upon base, that is delta x by delta t. This is average velocity, right? So that means the slope of AB line, this is A line, waypoint B point, slope of AB, this is average velocity. So this is important thing. This is the slope and it is the average velocity. So, okay, fine. Now, can I bring these A point, B point close to each other? So you would say yes, we have done this already. We brought this time T1 closer to T2 by making it T. And basically, we have selected these two time instants which are very, very close to each other. So if I keep bringing these two times closer to these two time intervals, that is T and T plus delta T, That is, if I keep shrinking the distance between these two time instants. This time instance is t1, this time instance is t2. So if I keep shrinking the time interval and make them closer and closer to each other, we use a very good word, which is called infinitesimally close. So infinitesimally close. Infinitesimally close means that they are very, very close to each other, but they are not a single instant. If they were combined, the denominator would become zero. This dt will become zero and it will be becoming infinite. That we don't want. We want them to be very, very close to each other and just a little bit farther apart. So this gives us the idea, okay, uh, we have arrived at 2 points which are very, very small distance apart. Okay. So that is the small distance apart is called infinitesimally close. So we will say that in this definition, that is delta x by delta t, or in this equation, if I make delta t very, very close to zero, so this delta x by delta t will become instantaneous velocity, right? So that is one thing which we have done, that we have brought these 2 points very, very close to each other, so that the average velocity is becomes instantaneous velocity, and we put a symbol called limit over here. So this is the limit symbol, limit delta t approaching zero. This is the instantaneous velocity. And for the final conclusion, basically what we have done is that these 2 points are brought so close to each other that this becomes A dash, this point becomes B dash. So I'll draw this again. Up till this point, it is clear what we have done. We have number one written the equation of instantaneous velocity, that is dx by dt, where x is position of the particle and t is time. We have come to the idea that the limit delta x by delta t, where delta t is approaching zero, is instantaneous velocity, because we are bringing these two times very, very close to each other. And now we understood the graph, that in the graph we have these times t1 and times t2. And we said that the slope of this graph is instantaneous velocity. This slope theta represents instantaneous velocity. If I take tan of it, tan theta. So tan theta is, oh, sorry, tan theta represents average velocity. That's what we have said. So how to make it instant? We make it instant by bringing these 2 points A and B infinitesimally close to each other, such that when this line, when it tries to cut these 2 points, right? A and B, it is cutting these two, this graph at point A or point B. So this is the line which is cutting this graph. So when the line has reached this point, where these 2 points are very, very close to each other, I'll take some time. A and B, they have arrived somewhere here. So this line is cutting the graph at points A dash and B dash. So when A dash and B dash are very, very close to each other, instead of cutting the graph at 2 points, it just touches the graph at a single point, right? So we have brought these 2 points so close to each other, instead of cutting the graph at 2 points, it is cutting the graph at a single point. This is what infinitesimally close means. Okay, and it may be somewhat mind-boggling at first, right? A dash and B dash are two different points, right? So how is a line which is cutting the graph at 2 points able to become a line which is cutting at a single point, touching at a single point? So this is what we are saying. A dash and B dash are very, very close. They are infinitesimally close. So when things are infinitesimally close, we can say that they are practically a single point. And this becomes the tangent. So this is what tangent means. So this is the tangent. So whatever the angle the tangent is making with the horizontal, this is theta dash. And just like we said, okay, tan of this line, AB line shows the average velocity. You would have guessed it right. Tan of this new angle, tan theta dash, which is the which this tangent makes, is the instantaneous velocity. Right. So this is what instantaneous velocity means. We we have to use the definition of average velocity, that is delta x by delta t. Now, by that definition, we have to take two time instants. And for an instant, if we take that definition, delta t becomes zero, and that is the problem. So what we do is that we basically shrink that time interval to as close to zero as possible, but not zero. So that is what we have done. We have taken delta t very, very close to zero, but not zero. So that makes average velocity instantaneous velocity. That's pretty good. And in that case only, the limit delta x by delta t, it becomes dx by dt. And this becomes instantaneous velocity. This is what differentiation is. Differentiation is finding the slope of curves like this. Basically, this is the curve I'm referring to, this whole curve, right? On which the particle's position is plotted. So this curved part, not the straight lines. The curved part, that is the curve. Differentiation is able to evaluate the slope of the tangent at different points. And it is also the instantaneous velocity of the particle at different times. So now how do I differentiate different curves? That is the question. So that we'll do in the next class. Thank you.